Hey everybody, welcome to your first class recording, or your homework recording I guess I'm going to call it. So we're going to try this year, as we've talked about in class, to try and minimize the amount of time that I spend talking to you in class and maximize the amount of time that you spend engaging with the material under my supervision in class. It's a technique that we sometimes refer to in the education world as flipping the classroom. So we're going to try this and see how it goes. Again, as we've discussed in class, it is essential that you actually watch the videos before class, because if you don't, this whole thing doesn't work. And then I have to review concepts that I already put into the video. So basically, don't be that guy or girl, and make sure that you're doing what you're supposed to be doing, taking responsibility for yourself outside of the classroom, so that we can make the classroom a place that all of us can get the help that we need as we go along. So, your first video deals with our introduction to mechanics. And as it says on the slide here, the study of motion. Mechanics is the basis of pretty much every physics class. It introduces core ideas that we will continue to use throughout the course, terms, concepts, applications that will become hopefully second nature over time, because they really are important to our understanding of everything going forward. This is how physics started. We look at the physical world around us, especially movement of things, and then we start trying to explain what's going on, why it's happening, and then use it to predict what will happen next. This starts on things that are available and readily observable, things here in the physical world. Back when Newton was developing these ideas, or Galileo, whatever, we're in that time frame. We're not talking about galaxies or planets or atoms. We're talking about the Newton or Galileo equivalent of buses, trains, basketballs, things of that size, things of that nature. So just know that this is the fundamentals, this is the beginning, and we're going to use this stuff as we go along. So, when we're looking at mechanics, there are really four things that we would like to know. Four questions that we want answered. And if we can answer these four questions, it will go a long way to accurately describing the motion of the object that we're dealing with. So here's the four questions. First, where? Where is this object that we're trying to observe, that we're trying to measure, that we're trying to predict about, whatever it may be? Second question, what? What is this object? Oh, sorry, buddy. That is not what I wanted to do. There we go. All right, next question. What is this object doing? Third question, what's going to happen next? What will this object be doing in the future? And then the fourth question, when are all of these things occurring? So we'll see here over the course of this presentation that the answers to these questions get assigned names. And these names are the terms that we're going to use going forward. So let's tackle the first question first. Seems like a logical place to start. Where is this object? So here is a picture of an iguana, some kind of lizard, whatever it might be. And perhaps this iguana is the coolest thing you've seen for a while, and you want to explain to your friend, hey friend, this is the greatest thing I've seen, this iguana is awesome. So your friend asks, well, where is it? You say, oh, it's sitting here on this desk next to me at the 20 centimeter mark of this ruler, which is great, except your friend doesn't know which desk you're sitting in, which room you're sitting in, or which ruler you're using to describe its location. So answering the question of where sometimes becomes a little bit more complex than it seems. But regardless, we refer to that where as the position of an object. The separation between an object and some reference point. And that's going to be a key point here for starting off, the reference point. Because the answer to this question of where something is might have different answers depending on who you ask. For example, if you're sitting at dinner across the table from your brother, your sister, your mom or dad or whatever it might be, and there is, let's say, mashed potatoes on the table. and somebody says, hey, can you pass the mashed potatoes? But you don't see them readily. Say, where are they? But depending on who you ask at the table, the answer to that question might be different. The potatoes might be on your right, but to somebody sitting across the table, the mashed potatoes would be to their left. Whereas if somebody was sitting on the adjacent side of the table, the mashed potatoes might be right in front of them. So the answer to that question changes depending on our frame of reference, or the coordinate system. And as it says here, it's the context in which we study motion. Now, that context can change in complexity depending on what kind of motion we're talking about. We're going to start with something that we refer to as one-dimensional motion, because it's the simplest thing we can talk about. If you think about math class, right, things in the world or things in math class happen in 3 dimensions, right, an x-axis, a y-axis, and a z-axis. We're going to start in just one dimension, which basically means we're stuck on a straight line. So, on that straight line, we have to do 2 things. We have to indicate a reference point, a point from which all of our measurements get taken. A lot of time the reference point might be the starting position for whatever object you're dealing with, but it doesn't have to be necessarily. It could be your location as you are observing a motion, or it could be some arbitrary point. As long as everybody's on the same page, it really doesn't matter. The second part of our frame of reference that we need to deal with is a directional system. As we just discussed with the mashed potato example, left and right doesn't always cut it, because left and right depends on your frame of reference, or where you're sitting, because your right hand and the direction in which your right is facing for you might be different from somebody who's flipped around. So we're going to have to do something a little bit more specific than left and right when we're talking about describing the position of an object. So, if we go back to our gecko example, or our iguana, whatever we're going to call this thing, one-dimensional motion, like I said, is basically a straight line. Or if you think about it from math class, it's the x-axis on a graph, and only the x-axis, right? When we add y and z, now we start getting into 2 dimensions and 3 dimensions, but we're starting in 1 dimension. The x-axis on a graph in math class is basically a number line. And if we think about our iguana moving in 1 dimension, we can think about him moving along a number line. A number line has some built-in reference point, specifically that 0 mark. Usually on a number line we go 0, and then there's 2 ways you can go from 0. You can go in one direction or in another direction. Let me draw a picture, hold on. All right, so if we talk about our number line, like we said, reference point generally is 0. And then there's 2 ways we can go on our number line. We can go this way, or we can go this way. And we distinguish those 2 directions on a number line with positive and negative. Mathematically, that's how we're going to start off in physics class as well. Again, limiting ourselves to 1 dimension, having one way expressed as positive and one way expressed as negative is enough to distinguish this side from that side. So, returning to our iguana here, if this point here is our reference point and he's over here, generally speaking, we usually call towards the right, the positive side. Doesn't have to be, but usually that's how it works in math class. And, we can start off that way here as well. We can say that this iguana, let's say the middle of his body, is 25 centimeters on the positive side of the number line. Or we can explain his position as positive 25 centimeters. Great. Now we've come up with a way to describe the position of the object. Sorry, let's do one more thing. Right? So if I want to draw a bad picture of an iguana, right? Let's give him some feet here. This might look more like an alligator, but I mean they're kind of the same thing, just a little bigger, right? So, right? So here's the 10 mark, here's the 20 mark, here's the 30 mark, not to scale. So here we could describe the position of this iguana as positive 25 centimeters. And if the iguana just happened to be, oh, not what I wanted to do. If the iguana just happened to be over here, right, that's a different position. It's still 25 centimeters or so away from the reference point, but it's on the other side. So we would refer to that as negative 25 centimeters. Different position, different way of distinguishing it, and on a number line, there's only two places that you can be 25 centimeters away from the reference point, here or here. And now we've come up with a way to distinguish those two places. So everything's great describing the position of an object, which is awesome unless sorry everybody, that iguana starts to move. Describing the position refers to, like it says, a position. Where is it right now? That's great, but things generally move. If nothing moved, it'd be pretty boring out here or in the universe and whatever. So we have to come up with a way of describing what if that position changes. And the term we use for that is displacement. By definition, the change in position relative to a reference point. So if we reference our iguana again, sorry, let me move this out of the way. If we reference our iguana again, he goes on a little walk. He starts off here, he ends up here. Perfect. Now we have to describe that. When we are talking about the change in position, when we are talking about the change in the position of an object, we need to know two things. If we need to know the change in anything, we need to know two things. We need to know the start and the end. That could be the change in position of this iguana, or it could be the change in temperature from night to day, or it could be the change in your bank account from before your birthday and after your birthday, right? Or it could be a change in your bank account from before Christmas to after Christmas, before you bought presents and after you bought presents. The change in anything is represented as the difference between the starting and the ending. Now, here in this picture, it's labeled as delta x. Hopefully you're familiar with that delta notation representing change. And whenever we calculate delta anything, right, it's a simple mathematical calculation of, hold on a second, final minus initial. So in this case, x final, where does this iguana ultimately end up on the x-axis, or the number line that we're using to represent the position, versus where did he start on the number line? So, according to me, this iguana started at the 24 centimeter mark. I know I said 25 before. This is an old presentation. I said 24 back when I made it, so whatever, okay, go with it. And then he ends up at the 85 centimeter mark. So 85 minus 24, we get a displacement of the iguana of 61 centimeters. Perfect. Except the iguana doesn't stay at that mark. He eats some leaves or whatever iguanas eat. I don't know, look at the winking lizard, I guess, in the cage there. It's celery and carrots and some other vegetables. But after a while, he turns around and he walks back in the other direction. The motion here is obviously different from the previous motion. One time he's going in one direction, one time he's going in the other direction. But if you recall, we had a way to deal with that directional system. And we said in a number line, because there's only two choices, we can use positive and negative to distinguish those directions. And that's what we do here as well. Describing the motion of this iguana, we're still looking at the displacement, right? The change in his position. And change in position, right, requires that we know where it starts and where it finishes and the difference between them. So we plug in some numbers here, right? This iguana, according to this drawing, right, ends up at the 12 centimeter mark. You can argue that if you want to, but I'm not there to argue with, so it really won't do you any good. It starts at the 78 centimeter mark, so we do some subtraction in this case, right, final minus initial, and we end up with negative 66, all right? The negative sign we've talked about is a way of distinguishing one way from the other. This trip of the iguana in this picture is actually a longer trip than this one. 65 centimeters versus 61 centimeters. The negative sign in this picture here is telling us nothing about how long or how big the trip is. It's only telling us the direction in which the trip occurred. Displacement and position as well are our first examples of something we refer to as a vector quantity. Vector quantities are important in physics because they describe two facets of a measurement. Vector quantities will tell us magnitude, or how big or how much something is, but also the direction, which way it's going. Vector quantities aren't so important in chemistry, if you've taken chemistry before. Most of the measurements you make in chemistry, temperature, mass, energy, things like that, they don't have a direction. There isn't mass one way or mass the other way. But in physics, when we're talking about this motion, talking about how big or how much of something is important, but which way something is occurring is also important. So vector quantities describe both of those things. How we describe the magnitude, that's generally a number. The direction, how we describe the direction, really depends on our coordinate system. In one dimension, a straight line, basically we're going to describe our direction with positive or negative, because that's how we distinguish one way from the other. We'll talk about other ways to do that when we move into 2 dimensions and ultimately 3 dimensions. We won't do that in this class, but the way we go from 1 to 2 is similar to the way we go from 2 to 3. Now, not every measurement that we use in this class is going to be a vector quantity. Sometimes it's enough just to know how much of something. When we are just looking at how much of something, we refer to those measurements as scalar quantities. Not scalar, scalar. Scalar quantities only indicate magnitude. They only tell us how much of something. So I kind of mentioned mass and temperature when we were talking about chemistry. In this class, in physics, we deal specifically with not only these 2 scalar quantities, but time is a very important scalar quantity that we deal with. If you recall the questions from the beginning of this, one of the questions is, when is all this stuff occurring? Time is a scalar quantity. The other scalar quantity that we're going to deal with a lot, not right away, but very soon, is energy. So, right, scalar quantities only tell us how much of something. All right, so we talked about the idea that when we are studying motion, there are 4 questions we're looking for. Where is the object? And then the second one is, what is that object doing right now? That's the next set of terms that we come across here, and we'll see that there's a couple of different ways we can describe that. So, the first way we can describe it is speed. Most of you are probably familiar at least with the concept of speed, but let's do a definition. Speed is the rate at which distance is traveled. Now, this word here, rate, Rate is a word that's gonna show up quite a bit in this class, and it always means the same thing. When we're talking about rate, rate is a way of describing a ratio, and that ratio always includes time. So, speed is the ratio of the distance an object moves and the time it takes to move that distance. Mathematically, we look at distance over time. All right? Probably you learned that back in pre-algebra, back in 5th grade or wherever it is. But it still applies here. Obviously, we're going to get into it a little bit more, but speed is a ratio of distance and time. So, right, if we look at measuring it, right, distance is measured in meters, time is measured in seconds, so we have a unit of meters per second. Now, we may or may not be familiar with this yet, but I'm going to do it right now. So, IB, not to be confusing, just to be a little more consistent with their measurements and the way they like to do things, right? They will not use the fractional notation. So most books in the United States, you'll see the unit written like this, meters per second or meters per second. But that's not how IB represents this quantity. They will represent this quantity like this, right? Oh, sorry, let's not do that. Let's do this. Okay. So, hopefully you remember from math class, when we have negative exponents are the equivalent of the reciprocal of that value. So, seconds to the minus 1 power is the same as 1 over seconds. Then, right, if we end up doing this, because, you know, these two are together, it means we're multiplying them, right? So that's the same as multiplying meters by the reciprocal of seconds, or 1 over seconds, and we would end up with meters over seconds, which is the same thing as this. It's just a different way of representing it. So don't get confused with that. I'll try to be consistent with it as I move along. I might fall back into an old habit, but hopefully that won't happen very often. So, getting back here, right? Speed, the ratio between distance traveled and time, all right? So here, if we were to look at this person running, I think it's a girl, it's a stick figure, but it's got a ponytail, not to stereotype boys and girls by having ponytails or not, but if I had to make a guess, I might say it's a girl. So here, if we're talking about speed, right, to describe the speed, we need to know two things. We need to know distance, we need to know time. So let me grab this real quick. Here, right, if I take it into this here, right? So we just learned that speed is a ratio of distance to time. Here, according to this stopwatch, it was measuring the time that it took the runner to get here. So the distance that she traveled, let's go with 50 meters, right? We should probably go 50.0 meters to measure properly on this graph. Oh, sorry, shouldn't do that. That's not measuring properly on this graph, or on this, according to this ruler. Let's go with 50 points. If you don't get that, it's okay for now. All right, and then according to this watch here, right, there's 6, so we'll probably go with 6.0 seconds, right? We do some math, and I've done this problem enough here that I know that the answer is 8.3 meters per second, or meters times seconds to the minus 1 power. Pretty straightforward, nothing too complex. Okay? It does get more complex, so let's talk about that situation. All right? And let's go back to, oh, hold on. Let's go back to our friend, the iguana. So here he is, and his 2 trips that he took before. Right? How fast was he going? Well, how fast he was going depends on 2 things. How far he went and how long it took him. So here, you can see that there's some clocks set up and the distances are the same as before. But there is one big difference that we noticed in the first trip that he took. One time he's going to the right, the next time he's going to the left. There's got to be a way for us to distinguish that, right? right? How fast he's going is great, but describing his motion also probably should include which way he's going, right? There's a big difference between traveling 35 miles per hour on Hilliard Boulevard to the west and 35 miles per hour on Hilliard Boulevard to the east, if you're describing the motion of an object, right? So we have to come up with another, or we have to define another quantity. And that quantity is velocity. Now, you may be thinking to yourself, wait, we just learned speed, and speed and velocity are the same thing. Not true. A lot of times they get used interchangeably, but they are not the same thing. So, definition. The rate of displacement of an object, which sounds pretty similar to speed, but there is a difference between distance and displacement. Remember that displacement we defined as the change in position from where you start to where you finish. Where distance is just the whole path that you take to get to wherever you're going, displacement depends on starting and finish line. Rate is included in that description, and we talked about a little while ago that rates are ratios where time is a factor. So the average velocity is the ratio between the displacement of an object and the time it takes to complete that displacement. Mathematically, we represent it with this notation. Now, I'm going to tell you in a little while, that IB does not use this delta x notation for their displacement. To confuse you, not really, but just a different way of doing it, they will use an S in this spot right here, which is not seconds, mind you. It's completely different than seconds. And so, but seconds doesn't represent time. It's kind of confusing. We'll work through it, but just so you know, it's kind of confusing. All right? So, average velocity, the rate of displacement, the ratio between displacement and time. Velocity is our next example of a vector quantity. If you hopefully you recall, because it just happened like 5 minutes ago, right? Vector quantities tell us two things, magnitude and direction. How fast and which way. That's important if we're describing motion, right? Yes, how fast it's going is important, but it's going one way or the other. If police are trying to apprehend a criminal, they need to know how fast he's going in a car, but also which way he's going. So they don't know that, it's not going to help them all that much, right? So velocity is a description of both the speed, the how fast part, and the direction that the object is going. So it's more detailed than our definition of speed. All right? So again, here's our iguana, right? Displacement we calculate by final minus initial, and we learned before that this was positive 61. Hold on a second. Grab this real quick. All right, so here's that picture again. We learned before that the displacement of the iguana here was positive 61 centimeters. According to the stopwatches here, 0 and 4, that took 4 seconds to do, right? Centimeters, yeah, it's not meters, but it's, it's not meters, but it's still a displacement measurement. So we do this here, and we end up, if I remember correctly, with 15.25. So we do some math and sig digs and stuff like that. We would probably round that down to 15 centimeters times second to the minus 1 power. All right. Here, we said this displacement was actually negative 65 centimeters. Looking at this, apparently I cut that off. There, 6 seconds, 9 seconds. Going back to my picture, so 65 centimeters divided by 3 seconds, and we end up with 20, Sorry about that, everybody. Computer decided it wanted to add a little bit. Okay. 20 point... Oh, crud. Hold on. Doing this in my head. 21.67 sig digs 22 centimeters per second to the minus 1. But because the displacement was negative, that comes out negative 2. Again, the negative sign doesn't tell us anything about how big or the magnitude of a vector quantity. It only tells us direction. Negative 22 is faster than positive 15. It's just faster in the other direction. So keep that in mind as we go along. All right, we've talked about where, we've talked about what. So our next thing is, what will the object be doing in the future? We refer to that as acceleration. We're going to get to acceleration more here in the next couple of days, but for now, the rate at which velocity changes. So, it's a ratio, but how much is the velocity of that object changing, or a ratio between the change in velocity by the time that over which that change in velocity occurs. Mathematically, it looks like this. Delta V over t, right? That's important because acceleration involves a change in velocity. Now, we will get to the quantitative analysis of acceleration soon enough, probably by the end of the week. But qualitatively, we can look at acceleration, and acceleration can take three forms. First, we think of acceleration as speeding up. That's what most people refer to acceleration as. And that's what the generally accepted version of, or sort of the description of acceleration is. And speeding up is acceleration because the velocity is changing. This cliff diver dives off the cliff. As he falls towards the water, he goes faster and faster and faster and faster, and that's acceleration. However, probably something that you guys are pretty familiar with, right? If you're ever running down the street, being chased by a gigantic boulder, you know eventually that boulder is going to slow down because of friction. Slowing down also fits our definition of acceleration. Acceleration requires a change in velocity. As that boulder is slowing down, its velocity is changing. It's getting smaller, but it's still changing. That is a change in velocity. That is acceleration. Now, there's got to be a way to distinguish, right, speeding up from slowing down. Guess how we do it? Acceleration is a vector quantity. Positive acceleration is different from negative acceleration. Generally speaking, positive acceleration is speeding up and negative acceleration is slowing down, but it doesn't always have to be that way, and we'll talk about those specifics as we go along. The third type of acceleration doesn't really appear, or at least on the surface it doesn't, but it definitely involves a changing velocity. So here's a picture of a carousel. You sit on your favorite horse, or if you go to the one at the zoo, it's got all those different animals on it. So you pick out your favorite animal, you go around in a circle, you end up right back where you started, which is fine, except the whole time you are going a different direction, right? Back when you were a kid, your mom and your dad and your grandma used to stand on the side of the carousel and watch you go at the Memphis Kiddie Park, if you've ever been there. But there was a time when you were looking at mom, and there was a time when you were looking at dad, and there was a time when you were looking at grandma, if those people were there. That means you had to be going in a different direction to face those different people. Because velocity is a vector quantity, and it has to tell us not only how fast something is going, but also the direction that it's going. Something that is changing directions or going in a circle like a carousel is accelerating. right? It may not be getting faster or it may not be getting slower, but it is changing its velocity because it is changing its direction. All right? Acceleration is a vector, as I mentioned before. Generally speaking, right, we talk about positive accelerations being speeding up, negative accelerations being slowing down. Not always, but generally speaking. One thing I do want to throw out there, negative acceleration and deceleration. Deceleration doesn't count. Let's refer to it as negative acceleration because that's really a description of what is happening. All right, so hopefully, right, over this brief introduction here, we've gotten the answer to these 4 questions. We didn't talk specifically about when all of these things are happening, but we did incorporate time into several of our definitions. That's that answer to the 4th question. So, where is the object? Position or displacement if we're talking about something moving. What is the object doing now? Speed or velocity, depending on how much we need to know. What will the object be doing in the future? Acceleration, right? Is the velocity changing? And then when are all these things happening? That's our time. All right, so tomorrow we will get started in class with applying these concepts, applying them to specific situations, and we'll build from there.